All right, guys. So there is one thing that I hope you actually had the time to think about. I will still possibly not answer it today. Remember that video with the monk, where you film the monk on day 1 and day 2, and the videos are of exactly the same length from 7 a.m. to 7 p.m. And what you're trying to prove is that there is a moment of time where the monk is in the same place in both videos. In other words, there is a moment of time where both videos look identical, right? So if you pause the videos at the same moment of time, you can imagine running them concurrently. There is a moment where video 1 and video 2 display the same paused picture. Have you thought about it, or you forgot entirely about this question? Carolina is smiling, huh?
Because I forgot.
Exactly, right? You're like squirrels, right? Too many math problems, you forget them, or just want to bury them away from yourself. All right, so they have to cross each other, guys. You see, so one thing about it, always try to think intuitively. Can you come up with a very intuitive argument for why the videos will have to display the same picture at some moment of time? Maybe they will display the same picture many times, but there is guaranteed at least one moment of time. And then try to explain that using the intermediate value theorem, because it involves the intermediate value theorem for a rigorous proof. Good? All right, so let's continue with the infinity lecture, and we might go back to that other thing later on. So you remember how we calculated that the sum of those numbers, the piles 2 to the power of 1, to the 2, to the 3, onwards, added up to -$2, right? So this technique is very useful. So there are many problems that are not necessarily so simple as this one, but you solve using pattern recognition. You understand what was the philosophy. So when can you solve a problem? Usually when you have a good idea. And a good idea involves, of course, truly understanding what is it that you're trying to accomplish. Okay, so philosophy really helps here, right? So the reasoning I produced is this. This looks scary. But even something scary is perhaps something. That's why I called it S, or maybe it's S for some, right? So if you get something, then I search for a pattern within that something. Remember how we did it, right? So we said something is equal to this entire thing. Could anybody tell me why I placed red parentheses after I skipped the first term? Why did I place red parentheses here? Will anybody remind me, please?
Because that's what you're gonna factor out.
Yes, but so in other words, that's very good. Just possibly one extra line to add to this comment. What's in the parentheses looks almost like the entire sum. That was my recognition. You understand that? I just looked at it, I say, okay, this entire thing, it looks like it contains itself in a way. So if I factor out the 2, I will see in the red parentheses exactly the original summation. Of course, because we go forever, infinity, right? So that's the same sum, and I can then simplify it. I can just say S equal to 2 plus 2S. As soon as you see, you ever thought about, you see how you get inspired to think like that? Have you ever thought about scary movies? And have you noticed that whatever scares you is not what you can see? So when they try to scare you, they don't show the creature. They show maybe an aspect of it. Why is that? Because really, as soon as we're able to make it as something, it's no longer as scary. The scariest things are nothing whatsoever, right? So something that is completely not known, completely unfathomable, that you cannot touch. And that's the scariest thing, right? So that's what I mean in mathematics. It is in part your biography, in part it's your inspirations, your thoughts. You can encode so many things in it. Or of course, it can just be symbols without any meaning. So then what we realize is the following. I cannot claim that the answer is -2 just by this argument, but I might say that if I'm getting something, that something is -2. Do you understand? The assumption that you get something gives you a -2. Good? Anybody here studies philosophy? Or at least, I mean, I'm not sure how seriously, but have you thought about philosophical stuff?
Yeah.
Yes? So mathematics is the craziest philosophy you can ever observe, right? If you ever want to truly seriously think about anything, that it gives you another eye, okay? And one of them is like when I teach complex analysis is the realization that if you believe in something, it begins to exist. Have you ever heard of Berkeley? Right? If you ever heard of Berkeley, Berkeley had this very strange claim that, well, how do you know that anything exists? And he says that you know that because when you touch or smell or look at something, because he was an empiricist, so you recognize that something is there by your senses, right? So and then by Occam's razor, he removes it and removes the existence of an object when you don't look at it. You understand? So Berkeley had this very strange notion. He didn't fully pursue it, but something exists as soon as you look at it, and then when you stop looking at it, then perhaps it doesn't exist. Okay. And of course, then he tried to say that it continues to exist when you don't look at it because God is watching or something like that. But in mathematics, you see that happening quite a lot. You understand? You might see that an object that you believe exists, it exists because of your belief in a way. At least it really, you can really see it mathematically. I'll show you examples if anybody is interested. That is the impression you get when you figure out the solution for the cubic equation, or at least the implications of the cubic equation to its implication about the existence of imaginary numbers. So Pavel, you have a question. Please tell me what's your question.
So the only reason this whole like factoring thing works, where you can like basically compress the whole thing into S, is because it's like it's kind of like the same idea as like infinity equals infinity plus 2, because it's still infinity.
Well, you're saying
like,
infinity, but I didn't call it infinity. Here I said it's -2. Okay.
But
so
it's like the same idea. Like you can only really like change it because, or like kind of manipulate it how you want it to, because it's basically infinity.
What I'm saying is that well, infinity is. I used, of course, the ideas of infinity implicitly. The fact that that you are right that basically we have 1, 2, 3, and I look at the cardinality. I can just say, okay, this starts from 2, 3, 4. It doesn't matter. It still is of the same size. So there are notions there of an actual infinity, but I actually haven't used it. Okay, this symbol, guys, is not a true infinity. If anybody is interested, we can actually have a conversation about what is infinity according to the theory of Cantor, which is the currently accepted theory for it. Okay, so for example, do you think there are bigger infinities than do infinities, all of them are of the same size? What do you think? Are infinities of the same size, just like or some infinities are bigger than other infinities? What do you imagine?
Like, what happens if I have infinity plus 1?
Well, infinity plus 1, it's not going to change it. It's going to be infinity.
Oh.
All right, but so are there infinities bigger than other infinities, or are they all of the same size? What do you think? It's a silly question, but I'm hoping that it's interesting to you guys, especially that you're young and you should be curious.
I remember in my outer limits of reasoning class, there was a whole concept about countable infinity and non-countable infinity.
Yeah, so you already heard of things like that.
Yeah, so it's like there's a difference, but at the same time, like to me, it's all the same.
Okay, so you say there are differences, but to you, it's all the same.
Like there's a difference when you like do what you do. Yeah, there's a difference. There's a difference.
Well, possibly. Again, you see, you can think of those symbols in so many ways. It's in some ways, the thing is, this type of thinking, for whichever reasons, or you know, if you believe in infinity or not, we will talk about it maybe at some other point. But it does give you answers that you can truly validate. You understand? So there is you see, if you look at this summation, what I did to figure out, remember the die problem, guys, right? I mentioned you toss a die until 5 and then 6 comes for the first time, or you toss the die until 5 and 5 comes up. Remember that question where you said it doesn't matter? You remember that game, right? So you're gonna pay your dues to the probability club by picking a die. It's a fair die. You're going to toss it until the pattern 5 and then 6 appears, or until 5 and 5 appears. Remember that question? And then you had to calculate which game is better. And you said that both games are the same, and you were wrong. The way I figured the solution to it is using part of it would be using this idea. It's a bit more complicated than what I'm writing here, but it's using that idea at the end of the day. You understand? It's using that same pattern recognition. And then you can verify empirically that my solution is correct. So the person that asked me this question, he simulated 100,000 throws of the die, 100,000, games, not throws of the die, just 100,000 games. And he found that the answers were as I predicted. They were tending to them. That's a limit, you understand? So this type of reasoning is very useful. Okay, so let's get back to, in other words, it predicts valid results, right? If you don't believe in infinity, somehow believing in it predicts the right results. That convinces you that perhaps there is something about it. Okay. Now let's talk about, and then in physics you have those properties that are also related to infinity. You understand that when you solve physics problems, you have uniform tension throughout the massless string. If you ever solve physics problems, I can show you a good book for that, right here, right? And of course, you might say there are no massless strings, but there are strings of very negligible mass compared to objects interacting with the string. So somehow this is important, right? Somehow when the mass is very low, then you have a very good approximation to that situation where the string is entirely zero. Okay. So here is, guys, this is not so important. I try to avoid using it, but you see sigma notation, okay? So the summations are written using sigma notation, and this symbol simply means what? You see where you have the k? K, there is, again, when people have a problem understanding variables. K here is just an index. It's an algorithm. It means write 1, then plus write 2, then plus write 3. So there is no K. It updates from 1 and onwards. You understand? To whatever you can put here a finite number. So this is just a very precise. If I just wrote, let's say, if I wrote 1 plus 2 plus 3, and then I asked you what's the next number, you would say 4, but that's because your pattern recognition, it tells you it's 4. It doesn't logically have to be 4. But if I write k1 to infinity of k, that means that is just I'm communicating the pattern entirely in non-ambiguous way. So can you see? So if I have 1 over 10 to the 1, 1 over 10 to the 2, 1 over 10 to the 3 onwards, I can write it in sigma notation very simply as summation k equal 1 to infinity 1 over 10 to the k. And I don't have to use k. I could have used I or any other letter. It just I'm just trying to capture the pattern here. Good. All right, and this is the summation only up to n. If I put n as the top number, you have 1, 2, 3, all the way to n. Good. Okay, so here is my next question, guys, right? So you see, you press in your calculator 1 divided by 3, correct? And you get 0.33333 in your calculator. How many digits it can display? It will display 0.333, okay? Now I mentioned what this means already. This means nothing else other than 3 divided by 10 plus 3 over 10 squared. This is just when you use base 10 decimal system, that's really what you're saying. 3 over 10 plus 3 over 10 squared plus 3 over 10 cubed plus 3 over 10 to the 4th and onwards. Tell me, please, verify that the sum is 1/3, or in other words, find that sum. Calculate that the sum is, if you obviously I already gave you the solution, it's 1/3, correct? I want you to now calculate it and show me that you understand why this is 1/3. That's great, great, Rafid. I'm really glad if you have. We will see it in a moment together. Hello, Brandon. Are you here? Brandon R. Eric Hanna. Are you here, Eric? Great. Hadi Harb. Are you here, Hadi?
Yeah, I'm here.
Great. Are you ready, guys? Great. If we're ready, let's see the solution. You see, guys, you will forget it unless you realize why is it that you can, why I do what I do, right? So you could have come up with this argument on your own. It's a matter of perspective, right? So here is what I do. I look at this entire thing and I decide to focus on everything but the first term. So I have 3/10 and everything following it looks almost like the original sum. Do you agree? It's not exactly, because the original sum starts with a 10. So all I have to do is I have to factor 1 out of 10. Do you agree? 1/10. Because then it will be 2 minus 1, 3 minus 1, 4 minus 1. I factor it out. And then what I have in the parentheses is exactly s, of course, assuming that without thinking about it too hard, that again, we have some notion of infinity here, is that the fact that I lost 1 unit doesn't matter. It doesn't change the sum, okay? So it's a sort of philosophy here. So this is exactly s. So I get this calculation. S equals to 3/10 plus 1/10 s. Do you understand? I simplified it. That's what I mean by something. This is this scary monster that I don't understand. But when I kind of grab it, if I give it a label, whenever you give it a definite form, right away it's no longer as scary. So 9/10 s is 3/10, and all I have to do now is just multiply by the reciprocal of 9/10, and I get 1/3. Everybody understands? Let me try to give you one extra sum just to be sure that you do. So suppose that I asked you to calculate this. So the number is 3 divided by, Nassim, please talk to me. Go ahead, what's the question?
Yeah, Professor, how did you get the 9/10?
Okay, 9/10, give me a second. Yes, 9/10, very simply, look at it, s, and here is 1/10 s. What happens if I take s minus 1/10 s? In other words, if you take something and you subtract 1/10 of it, you're left with 9/10 of it. Or if you prefer, just move it across. Let me write it. Move it across. So you have s minus 1/10 s. Yes. What is that? You can factor out an s, and then you have here 1 minus 1/10, and that will give you 9/10. Do you agree? So this is just algebra, but when you do this algebra, there is always some sort of thing that I think you don't understand. What is this? If you take something and you subtract 1/10 of something, then you're left with 9/10 of that something. Do you agree? So I don't even factor or do anything like that. I just know that something minus 1/10 of something is what is it? It's 9/10 of something. Remind me, by the way, guys. I can tell you afterwards. Children's story. Pretty interesting one. I wonder what you will think of it. I might forget. So if you're interested, remind me.
Is it with the rice? I know what we're about to say.
What I'm going to say with rice? What
yeah, like on the chessboard, like you have like one grain of rice.
No. I already mentioned that, of course.
Oh, never
chessboard.
mind.
That was the first lecture 0. No, it's an entirely different story about dividing inheritance. But if you are interested, I will let you. We can talk about it later, perhaps. Right. So now I would like to ask you the following problem, guys. So suppose that you had to calculate 3 divided by 10 plus 4 divided by 10 squared plus 3 divided by 10 cubed plus 4 divided by 10 to the power of 4 and onwards. You understand the pattern, right? It goes 3, 4, 3, 4, 3, 4. I want you to tell me what is this number. Yes, Brandon, it's 0.343434. I want you to tell me what it equals to, a fraction, because when you put it in a calculator, that is just the same as the summation. It's just another way of writing the sum. You're not adding anything, right? You're not giving any more understanding to this number. It's an infinite sum. So when you saw 0.3333, how do you know it's 1/3? That's what we calculated here, you understand? I can show you afterwards how machines or how you can actually do that if you're interested. How you can figure that 1/3 is 0.3333 forever. Yes, Alan, but that doesn't give that's the same as writing the summation. 3 point set a repetition, but what is it equal to? What number? What fraction? Well, that's weird looking. Make it give me a simple. It's not 1.3. It's not obviously. Wow, it's not 1/3. It's definitely not 1/3. Guys, you don't need to guess, right? Do you understand the idea with which we solve this problem? Well, Alan, you're close, but it's not quite right. No, James, you made a number bigger than 1. It's impossible. Okay, Pavel, good. Guys, so you should trust your instincts, right? First of all, what's the idea? Don't try to remember the procedure. That if you remember the procedure, it means you have no idea what you're cooking. So how are you doing, guys? You're figuring it out? Is there anyone brave here that would like to walk me through the solution? Oh, I knew Pavel will volunteer as a tribute. So, okay, Pavel, go ahead. Tell me how to solve this problem. What do you do? And why?
Well, how exactly? I don't know how to solve it, but I got a kind of clue, and I was testing. I was doing guess and check, but I understand why it's 34.
I mean, guess and check. I mean, yeah, you might press in your calculator some values and figure it out. How do you figure it out exactly? So there is.
I can explain why it is 34 over 99, which is kind of like reverse engineering, I guess.
Okay.
What it does, well, when you would divide something by 99, you basically remove every other decimal, the value of it. Like if you do 1 divided by 99, like I kind of played around with some numbers, and I did like 1 divided by 999, and it basically makes it so it repeats itself every 2 decimals. If it's like 999, it repeats itself every 3 decimals.
You sound like somebody. I asked a person, could you hammer in the nail into the wall and you build me a spaceship? Right. So yes, you can play around, and that's very intelligent. But I'm asking just how do you look at the summation and right away know what the answer is, right? So what you're saying is interesting, but playing around, I can make it a different number. How do you?
Because you're removing 1/100th of every other decimal is less than 1.
Complicated. Okay, so look at this thing. What's the idea? It's an infinite sum. Is there a similarity pattern, right? So look at it, 3 4 3 4. So after the 3 4, here we go. This thing looks very similar, no? I skipped 2 terms, right? Why do you have to stop after the first term, right? The pattern is 3 4 3 4. So I skip until I begin the pattern again, and now it's 3 over 10 cubed, 4 over 10 to the 4th. What do I want to factor out?
1 and over 10 squared.
Exactly. So what do we have? You have S equals to 3 divided by 10 plus 4 divided by 10 squared plus 1 over 10 squared times S. Do you agree? It's just a slight, all it is, guys. You see, that's my point, right? It should be the same problem to you. If you learn it correctly, many questions here are exactly alike. I will try to train you up with that, but it's really just a matter of recognition. If you realize that there are many problems that are exactly alike, or almost all of them, so by the time you know the material really well, it looks to you like 1 problem, or maybe at most 2 problems, this entire material. Good? So we have that. Now, what happens now? What we do now is I'll write it above, so because I'm out of space there. So I can write it as S minus 1 over 10 squared. So that becomes 99 over 10 squared S equal to, I can have the common denominator. So that would be 34 over 10 squared, right? So that means that S is 34. I can just cross out the 10 squares here. So it's 34 divided by 99. Good? Very easy, right, guys? Nothing. So what you're saying, Pavel, first of all, guys, you should not be worried. You can talk to me. What Pavel is saying is very interesting. It's very smart. But you see, too complicated for this particular problem, right? You can just write away and you're done. You understand? So what you're noticing is very interesting. You might be like a natural born number theorist, right? So you can see patterns in numbers, but for this, the easiest idea I can think of is pattern recognition. You realize that if it's infinite, then skipping a few terms, you can pick something up. Of course, it works when you can see a self-similar pattern. You understand? When you can see the entire sum buried within itself, so to speak. Do you understand how I solved it, guys? So, you know, you're quiet. I cannot see the entire class. A very strange aquarium type of feeling that I have from you. You know, so hopefully, right? But okay, I have only 2 people. So the others, what? They lost consciousness. Let's try another. There will be plenty to try. You can write yourself a question like this. You understand? You don't have to even wait for me to write one. You can write yourself a question like this and test it. And then how do you verify it's correct? Well, you can press in your calculator 34 over 99, and what do you get? You get 0.3434 forever. You understand? That's how you know that's correct. So let me erase all that stuff and move on. So we have plenty of interesting problems. Has anybody been reading my notes? Do you read them? I see you have poker faces. My God, you have faces that you should be so good with probability. I know that you haven't. You don't do enough, guys. I know you haven't, right? All right, guys. So here is my next problem. Right? We can practice this afterwards again. Here is the next problem. And let's see if you can solve it very fast. And then we'll solve it in 2 ways, so to speak, right? So you roll a fair die until either the number 1 or the number 6 comes up. Do you understand? You continue throwing the die until you see the number 1 or the number 6. It's similar to the problem I asked, except much easier. Remember, with the 5, 6, and 5, 5, right? So you roll the die until you see 5, and then until you see 1, and then you lose the game, or you roll it and the first thing that comes out is 6, and then you win the game. Yeah? Do you understand what I'm asking now? So I'm asking you, what's the probability that you win the game? So think about it, and I want to hear your comments. Funmila, are you here by any chance? Funmilayo here or not?
Hello?
Ah, good, good.
You wanted me to answer a question?
No. I just, when there is a box, I just make sure that people are not just opening the browser and leaving.
Okay, thank you.
Sure. All right, so Brandon says 1/2, like an easy answer. Okay, Brandon, that's nice. Alan says 1/3. Let's see what other people say. Rafid says 1/12. Interesting. Okay. And this is also something, it's a question of philosophy, guys, right? So you can solve questions in the hard way or the easy way, depending on your philosophy, so to speak. What do you understand about life? Four over 6. So 4/6 can be simplified to 2/3. Rachel Minkovich says 1/6. Hadi says 1/5. Well, who else says what? Some people say 1/6. 1/2, because Muhammad says 1/2 because there are only 2 options. Okay, let me give you an example. You will either live to be 1,000 years old, or you will not live to be 1,000 years old. There are 2 options. So the probability that you will live to 1,000 is 1/2. Congratulations. Good, guys. So, but your answers are very, and you know what it reminds me of? You know of this ABBA song, the winner takes it all, right? The gods will roll a die, the gods will roll the dice, their hearts are as cold as ice. So why is that a good song to remember? Because that
All
solves
those
the
were the
problem.
lyrics.
Huh?
But then again, I don't listen
Sorry?
to ABBA that much.
Sorry?
I didn't know those were. Sorry. I didn't know those were the lyrics. But then again, I haven't listened to ABBA.
We can listen to it afterwards to verify. I mean, I don't listen to ABBA, but this is one song that I do like. I can show you some songs that I like.
It's one of my least favorites, to be honest.
ABBA or this one?
The song.
No, it's I don't know. You're too young or maybe too hopeful. That's maybe why it's your least favorite.
No, I'm just a sucker for music. It's one of my least favorite things.
Ah, you don't like music.
Not at goddamn all.
That's sad. I cannot. It's very sad, truly, right? Music is one extra sense that you have. I want to sing, like, so I would say with the voice of a poet, but I don't have a voice. So guys, okay, let me just give me a second. It's a bit warm here. Okay, so why is that the case? So do you understand what is fair? Fair means actually not necessarily something too nice. Fair means indifferent. Indifferent, right? So look at is the die in favor of giving you a victory or giving you a loss in this case, right? Is there any favor to end the game with a 6 or to end this game with a 1? You understand? So some of you, and actually Rafid, I think, right? You said there are 2 options. You forgot to mention one extra condition. There is no favor which option, right? So to live 1,000 years or to not live 1,000 years, there is a favor, unfortunately, to not live 1,000 years. That's favored. You understand? So some options might be favored, but if you have 2 options and none of them are favored, then they're equally likely. You understand? You're with me, guys? You understand that? Why do you say that a coin lands on heads or tails with probability 1/2? What you're truly expressing is that the coin is indifferent. And I really like the German word for indifferent. You can remember it, gleichgültig, indifferent. Die Münze ist ganz völlig gleichgültig. The coin is entirely indifferent, right? It just captures it. Gültig means like fair or valued. Its value is all the same. It's indifferent. Just like I remembered yesterday, because yesterday, you know, it was my birthday, and then you know what is indifference. You truly understand what's probability. Okay, so 1/2 is the answer. Here is the solution in another form. Okay, guys. So if you are winning this game, you will win it on either first time you throw the die, or on the second trial, or on the third or fourth, or onwards, right? So it will be over eventually. So WK is the event that you win on the kth round. K is just arbitrary round. You understand what I mean? I need to figure out what is an arbitrary round. So that means that I neither won nor lost on the previous rounds. That's what this is saying. And I won on the last round. When you are doing probability, what you're truly doing, you're counting possible universes, right? Especially if those universes have equal likelihood of outcome. So why is the probability that the die lands on 6 just 1/6? It's because there are 6 universes. It's 1 out of 6 universes. Universe where the die lands on 1, or the universe where the die lands on 2, or on 3, or on 4, and each of the universes has equal likelihood of actually taking place. You understand? So in here, I count the possible universes where I neither won nor lost, in limbo. So there are 4 universes like that, because 1 is the universe where I get 1 is not there, and the universe where I get 6 is not there. So there are 4 possibilities for this universe, 4 possibilities for that, for the next, all of them, right? There is only 1 possibility where I win in the last universe. That's 1 here, okay? And the denominator is the total. This is not division here, right? This is the total number of universes. 6 universes that I can get on trial 1, 6 universes on trial 2, and onwards. So the answer is that I win on the kth trial with probability 4 divided by 6 to the power of k-1 times 1/6. I kept the 1/6 as separate because then the pattern is easier. You understand? And so now I have to add up or sum over all the possible universes. See, because all the possible trials, right? Do I win on first trial or second trial or third? That's what the summation is. K is the kth trial. Abstract reasoning, hopefully not above your head. It's very simple, right? You use abstract reasoning all the time when you make a statement. Let's say people are mean. Like, oh my gosh, people are mean. What you mean by that is for every person, that person is mean. So it's abstract reasoning. Okay. So here, this is the summation. Its probability equal to 1/6. That's the probability you win right away, plus the probability you don't lose on the first round and win on the second. So it's 4/6 times 1/6, plus this is the probability you win on the third trial, on the fourth trial, and so on, right? So what I can do is I can again put my brackets around everything but the first term. And what do I factor out? Look at it. I need to start with 1/6. So I factor out 4/6 here. I factor out 4/6. And now I get the summation to be 1/6 plus 4/6p. And then when I simplify it, I get 2/6p equal to 1/6. So p equals to 1/2.
I followed up until, all right, so the first part, why is it 1/6 plus the p, like the rest of it?
Why is it the red? Well, because look at it. The summation here is infinite, and when I factor 4/6, it looks like the original thing. It looks like the original sum. The probability is the sum of those possibilities here, and then what I see in the red parentheses is the original sum. Do you see that? Look at it. It's 1/6 plus 4/6 times 1/6 plus 4/6 squared, etc. So if I factor the 4/6 out of the parentheses, I get the original sum.
Okay.
Well, so Pavel, the point is that you can see the infinite sums give you that result. Here, it's not the quickest reasoning, correct? In other problems, it is the quickest reasoning. Like for example, if I said, or at least try to come up with a better one. I asked, let's say, about which game is better, 5-5 or 5-6. Try to figure it out, right? Any other way. It was only easy because intuitively, you can understand that there are two possibilities. The game is over with 1, or the game is over, or the game is over with 6, and there is no preference. So it really reduces to the coin problem, heads or tails. That's only coincidental. Okay, so Christian says, why 4/6 for p? Well, look at it. This is the summation that I get. This is what this means. You understand? I calculate for the general winning at the kth level, and that's the number I get if I win on the kth level. It means if k is equal, it's a pattern. You see, if k is equal to 1, the probability is 1/6. If k is equal to 2, the probability is 4/6 times 1/6. Do you understand this thing, guys? This is just calculating the probability of winning with the specific requirement on which throw of the die. So this is on the kth throw of the die. That's the probability. Do you understand when I say kth throw of the die? I'm not sure if you process that, guys. I hope you do. No, Christian. It should be 1/2 the full answer. Look at it, guys. Do you understand what is this k? You're very quiet. Do you understand the k? Write in the comments if you do or not. Okay. Miri Umi says yes. It's all, you see, that's what worries me, guys. You really need to, you have that ability, but somehow you neglect it once it comes to mathematics. It's just, I speak about a generic possibility. Understand? I found a pattern for a generic possibility. K is the time you win. So if k is equal to 1, that means you win on first throw. If k is equal to 2, it means you win on second throw. That's all it is. You understand? And mathematics gives me the ability to speak of all the cases simultaneously. Right? So that's the pattern for, and then I just have to add over the cases because I either win on first trial or second trial or third, and that's the summation I develop. You understand? And then from the summation, I can now use the previous result. I factor out 4/6, and I have the summation. Good. I can give you more complicated problems like that if you're interested, but you know, let's go onwards for now. Here is a very famous problem. So I will show you the picture and listen to me, right? It's written over here, but the picture says it all. Okay. So I think it emerged in the late 1940s, and you have two cyclists. They are 20 miles apart, and they are traveling at the same speed, 10 miles an hour. You see the blue arrows? They are traveling towards each other. Good. Now on the nose of one of the cyclists sits a fly. And as soon as they begin moving, the fly takes off and it flies at 15 miles an hour from the nose of one person to the other, back and forth, until the two cyclists touch with their noses. Okay, understand? The noses will touch, and then the fly is moving between them. So the question is, how much distance will the fly cover as they move around? Do you understand the question? So they are moving towards each other. Here everything is drawn, 10 miles and 10 miles, and the fly is moving like my red cursor, back and forth, right? Until they touch their noses, always at 15 miles an hour, either to the left or to the right at 15 miles an hour. So Pavel right away gives an answer. Pretty interesting. Have you heard of this problem before, Pavel, or because it's halfway? So Alan says 7.5. Okay. Let's see what you say, guys. I wonder also if you figure it out correctly. In other words, you can fall down the stairs, and it might put a disc back into your back, so you actually get better afterwards. It happens sometimes, right? So it definitely happens in mathematics. In other words, you can have fool's luck. Oh, David Wang, are you here? Okay, great. Nassim? Nassim, are you here? Ahad, are you here? Great. All right, so any new ideas? I'm not sure. So Pavel suggested something. Pavel, are you there, or you left somewhere for a moment? So for the first question, guys, as we're waiting there, how many times do you think the fly travels back and forth? How many back and forths does the fly perform? In other words, here is one direction, second, third, fourth. How many times? So Nassim says 2. Okay, what about the rest of you guys? How many times is the fly going back and forth? June says infinitely many times. Oh, great, Pavel, you are back. So we were discussing this. We were asking how many times does the fly go back and forth between the nose of one person and another? Boom, 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 boom. How many back and forths? It's a simple question. Yes, guys, do you understand? Infinite sounds about right. It is infinity, and you can easily convince yourself. I'm not gonna do it right now. Think about it, right? It's infinitely many times that it goes back and forth. Pretty weird, correct? So the way von Neumann solved it, von Neumann was a big genius. Actually, I have a translation of one of his videos. I worked on it quite a long time ago. So Eric, no, it's not once. It's actually infinitely many times that the fly will go back and forth. So no limit, just back and forth infinitely many times. So when it was asked of von Neumann, he solved it instantly. And then the person that asked him said, oh, great, you right away could see the trick, the clever way of doing it. And he said, what do you mean? I just solved an infinite series. So what von Neumann did is, in symbols, possibly what I wrote over here. You see, I just calculated it for any distances, blah, blah, blah. I'm not going to go over this explanation because I think we will spend quite a long time dealing with it. That's how I solved it. TK is the time for the cave trip. So basically, I imagine I'm going to watch the fly, and then I will pause the video as soon as the fly is on the nose of the second cyclist, and that's T1. Then T2 will be when it's back on the nose of first cyclist. Then T3 is when it's back on the nose of the next cyclist, and so on and so forth. And that's the formula. This is what I get, guys. That's how I solved it. You see, this is what you get, and the answer is 15. Okay, now what is the clever solution where you can avoid using infinite series? This I will explain to you. The cyclist. It will take the cyclist how much time to meet? How long does it take the cyclist to touch noses? It takes them exactly 1 hour to touch noses, correct? How do I know that? It's because distance is 20 miles. Look at it. How do I know that? Distance is 20 miles, correct? Now, when the cyclists meet, that means that both of them covered a distance of 20 miles. So the distance covered by cyclist 1 and cyclist 2 together is 20 miles. They cover each their own section, correct? Now, in any given moment of time when you press play, the amount of distance covered by this guy will be t times the velocity, so t times 10, and this will be also t times 10. So it will be t times 10 plus t times 10, it will be twice. So in other words, 20 times t, right? So t is the amount of time until they meet is just 20 divided by 20, which is 1 hour. So they will meet in 1 hour. I hope you understand that, guys. If not, we can talk about it again. So they will meet in 1 hour, and all this time the fly is moving at 15 miles an hour. We don't care if it moves forwards or backwards. It just moves at 15 miles an hour. So it will fly 15 miles. You understand? But it will actually not fly 15 miles in one direction. It will fly 15 miles like this. You understand? It's the situation there. So that's not a trick that von Neumann noticed. Of course, he solved it instantly, and that's not a trick I noticed when I first heard of this problem years ago. I figured to do this. See, blah 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 blah, and I got the answer. But I'm not sure if the numbers were the same. It doesn't matter, right? You solve it in formulas. That's the general solution. Good. It doesn't even happen to be. You can change the velocities. You can make it harder or easier and whatnot. So here is my next problem. So Carolina is asking, why is distance traveled 20? Doesn't the distance traveled depend on the meeting point? Well, again, distance traveled, look at it. Wherever they meet, they from both directions, they trace the full line. Do you agree? So when you walk from, one person walks from here, the other from here, when they meet, no matter with what speed, they both covered the full distance, right? So the distance covered by person 1 and the distance covered by person 2 together add up to the full distance.
Wouldn't it be the middle point if they're going the same speed?
It will be the middle point in this case by symmetry, yes. But so you can say that with the time when they meet, you can solve it differently here. But that's because they travel at the same speed. Usually, if they don't travel at the same
Yeah.
speed, it will not be the middle point, right? You just add the velocity of one person to the velocity of the other, and that will be the velocity with which they erase the distance, right? With which they close to, just remove the distance. So the midpoint will be 10 miles, right? So it's 1 hour. You can think of it this way as well. The middle point is where they meet. It will be 10-mile distance. So how long does it take this guy to get 10 miles? He's traveling 10 miles an hour. It will take him 1 hour. So you can think like that, Carolina, pretty well, right? By symmetry. But in general, they don't have to travel at the same speed. So in general, it would be velocity v1 plus velocity v2 times time equal to distance. So time equals to the distance divided by sum of velocities, which in this case is twice v. Good. Here is my next question. So the reason there are videos on my channel, some videos actually that, where I was in class. So I was thinking that, I was cheery and all bubbly when I was younger, but then I think age is getting to me, soon I'll be an old and grumpy professor. So I was saying that to my brother, and he said, well, why not just record the videos? And he came and he recorded some of the videos. I was thinking maybe he will learn the mathematics, but all he was doing, he was actually monkeying me, right? He was just, trolling me. So one time he comes home and he says, well, I'm interested in infinity. Will you help me? And then we drove 2 hours, 2 hours upstate. He parked our car next to, he parks it next to a 2001 Infiniti QI 30. And he just brought me there to drive the other car back, you understand? And then he also bought something that looks like this device, okay? So it's a device that you use in your cell phone. It's called a fractal antenna. Maybe I'll show you a picture of it before we go there. He actually brought a triangle version of it, but you have, I suppose maybe still you have it, or maybe it's only in the older phones. You see this picture, guys? You see this device? That's the antenna that your phone is using. That's increasing reception. It makes it, it makes the reception far better than without this device, okay? Or this is the triangle factor antenna. So I will show you how to construct this device and possibly how to make lots of money. Okay, here is the construction of that device, okay? So what you do is you take a square sheet of metal, you see it? And you subdivide it into 9 regions and you puncture out the middle region. How much area did I puncture out? So from this metal, I puncture out the middle square. How much area did I puncture out? Can you tell me? This is 1 by 1.
1 out of 9.
1 over 9, Pavel, correct. You see why it's 1 over 9? Because it's very simply because it's 1/9 of all the other squares. Area is just you exhaust. The 9 of those squares make the big square, so it's 1/9, correct? Good. So you puncture, and then the next process, you have 8 remaining squares. Each of them you puncture in the middle. This is 1/9 of the 1/9 of the square. So what's the area of this small square? Exactly, 1 over 9 square. You all see that, guys? It's 1/9 of a 1/9. The reason it's 1 over 9 square is because it's 1/9 of a 1/9. Is it right? And then the next one is you have more of those squares. It's 1/9 of 1/9 of 1/9. So this tiny one is 1 over 9 cubed. Good. So how much material do you save? The material that you puncture out, you can reuse. It's not part of the antenna. You can melt it and have another, and just add it to recycle it, basically. You understand what I'm saying? You can recycle this material. So the question is, how much material do I recycle? Yeah, you continue doing it forever, of course, right? The true fractal antenna, you continue puncturing on and on and on. Let's see, can you see the pattern? How much material do I recycle? So there is 1 over 9 plus 8 over 9 squared, because we have 8 of them, yes? Plus how many of the smaller ones, etc. So figure out how much material do we recycle. So Nassim says that we recycle 1 out of 72 of the entire material. Let's see what the others say. You understand the question, yes, guys? We're trying to figure out how much material is recycled. In other words, how much material actually goes into the antenna. So we know this 1/9 is recycled. This 8/9 squared is recycled. So we at least have 1/9 plus 8/9 squared. And then we have extra smaller holes that we recycle. So Pavel says 10/81. Interesting. Pavel, you speak Russian, don't you?
No, just full. I'm fluent in Polish and I'm learning Russian by class.
Because your name sounds Ukrainian.
It's Polish.
Okay, I see. Yeah, maybe. I thought maybe Polish or Ukrainian.
Close.
I guess I missed it. Okay. You do look more Polish than Russian, but your name, I said Uk, right? Usually is Ukrainian. Maybe with a different spelling. All right, guys. What about the rest of you? Did you fall asleep? That's good, Rafid. What are we doing? we are figuring out exactly, right? No worries, Muhammad. So again, you see this sheet of metal. It's actually a system that I'm not sure if currently you use it in your cell phone or some other antenna is there, but that used to be definitely a fractal antenna in your cell phone. And we want to know how much of the material is needed to construct this antenna. So what we have is we have a square of metal 1 by 1, and we'll see, Pavel, right? Good that you're asking, right? And then we puncture the middle nines, and then we have 8 remaining subsquares. We puncture the middle nines of each of them, and then we in each of this system we have 8 remaining subsquares, and we puncture the middle 9 of them like this, and we continue doing that on and on and on. Yes, does it make sense? The question is how much material is used in constructing this antenna, or how much material can we retrieve? Because this metal sheet that we puncture out, we can mold it or melt it and build another square of metal, right? So okay, let's start to do it. Okay, guys, are you ready? So I'm not sure about you. You see, those things, I mean, are hunting my nightmares. I will tell you afterwards maybe why. At the end of this lecture, I will show you a little bit about what those things are. So here is the situation, guys. How much am I removing? I'm removing 1/9, correct? Plus how much here? 8 divided by what? So 1/9 plus 8 divided by what? Okay, Rachel, thank you for your number. Rachel says 1. So let's see for a moment. Okay, so we're there together. So I'm taking, Alan says 8/81. So first question is, again, we're doing it together, guys. 1/9 plus what's the area of, what's the combined area of those 8 subsquares? What is that? No, I understand, Rachel. I understand what you were saying. That's very good. I'm saying, we will see if you are right. So the small square I puncture here is 1/9 plus 8. What's the area of those squares, guys? Come on. Come on, come on, come on. You can do it. Victoria, factoring will be involved very soon. Don't worry. No, Alex, no. It's 1/9 of 1/9. So it's the area of one of them is 1/9 squared. So it's 8/9 squared. And then we have 8 here plus 8 here, 8 times 8. So it will be 8 squared over 9 cubed next. You following? Yes, it's not good to solve it. Just notice the pattern. Here is the pattern, guys. So first is 1 over 9. Next is 8 over 9 squared. And then the next will be 8 cubed over 9. Sorry, 8 squared over 9 cubed. Do you understand why? So the area of the smallest rectangles, you have 8 of them here and 8 of them here. 8 times 8 is 8 squared. What's the area? It's 1/9 of 1/9 of 1/9. Do you understand how I figured that out? Look at it. This is 1/9, and this is in proportion 1/9 of it. So it's 1/9 of 1/9. So it's 1/9 squared. So we have this summation. Area is equal to the summation, and then what do I do next? You see, I have 1/9 plus 8/9 squared plus 8 squared over 9 cubed plus 8 cubed over 9 to the 4th. And then what do? I want to put parentheses around this part, right? I put parentheses here. Do you understand why? Because I can make this in parentheses look like the original sum by factoring out 8/9. Do you agree? Factoring out 8/9 will make this, because I wanted to begin at 1. So factor out 8/9, it will be the same sum here. So what we have now, is that a is equal to 1/9 plus 8/9a. Solving, we just move it across. We have 1/9a equal to 1/9, or a equals to 1. And Rachel was the only person to figure it correctly. Now that you appeared, Rachel, I really congratulate you. I was hoping it would be you because you should change it. It's not Minkovich, it should be Minkowski. And then he's a great mathematician. You can check him out. Although he was German and mean. Apparently, he said something to Einstein. I forgot what he said about him. Something that he's a wretched dog that cannot do math. It's true. Good? Are we there? Okay, guys. So this is just a preview. We will return to more paradoxes later on. Let's now talk about limits at infinity and what they mean. Okay, so we already know what it is to take limits as x goes to a finite number a. It just means that I plug into the function a-like numbers, correct? And now, what will it mean if I take x and move it to infinity, which means x is a number that grows. We're just plugging in numbers that are bigger and bigger and bigger and bigger. And I want to see what happens to the function, okay? And if I take limit as x goes to minus infinity, I just plug negative numbers with huge magnitude, right? So the magnitude grows and the number is negative. That's x going to minus infinity. Let's see how good you are without any explanation here. What's this limit? Calculate limit as x goes to infinity of x squared minus 1 over x squared plus 1. What's the limit? So thank you. All right, let's see what you say, guys. And of course, not only the solution, but always why. It might be that you're just lucky and you have beginner's luck. That's nothing more. So Christian, you say minus 1 and 1, but only when x goes to infinity, right? All right, what's the limit if x goes to infinity? Come on, be brave, guys. Okay. No limit. When somebody says no limit, they remind me of Tsvetaeva. She knew no limit. Good poetry. I should teach you some. Okay, so let's do it together. Still a first try, guys. Eric Hanna says 1. Denominator 0. Sure, we cannot without using imaginary number. We cannot, but we're taking limit as x goes to infinity. Right. So here is what's going to happen. So beginner students typically, I'm not sure if it's true. That's just my assumption, right? So okay, what do you do? you plug this value, right? So we take infinity, you plug the value. Plug the value, infinity squared minus 1 over infinity squared plus 1. Well, that's infinity. Denominator is infinity. So infinity over infinity is 1. Is this the right reasoning? And if no, then tell me what's wrong with that reasoning. So if it's not the right reasoning, what's wrong with it? Infinity is not a number ratio. That's very good. Even though, confusingly enough, in complex analysis, it's very much a number. That's the only subject where I can say right away it's a number, right? So it's like the lesson one. There is like a very funny thing. I think it came in 2009, the lesson one. If you ever search for it, a human giant, the lesson one. So this is the problem, right? So not only is it not a number, by the way, even if it were a number, you don't plug a number in when you take limit, right? You are plugging in large values of x. So the thing is, this is just saying that numerator is dynamically growing. It's becoming longer and longer and longer. And the denominator is doing the same thing. But they don't have to do the same thing at the same rate, you understand? So for example, volume grows faster than area, surface area. You know this, right? That's why elephants have those big ears. They need to cool themselves off, because if you're a very large animal, you have much more volume than you have surface area. If you are a very small animal, you have much more surface area than you have volume, okay? So they don't necessarily grow at the same rate. Even though everyone who said the answer is 1, they are correct. And here is one way to do that properly. Look at it. What can I do here? I can factor out x squared from the numerator. Do you understand what it means to factor out x squared from the numerator? You might think of it very simply as, well, if I write x squared outside of the parentheses, then here I will have x squared divided by x squared minus 1 divided by x squared. Understand, when you factor something out, you just divide by each term from the parentheses, right? The same thing, right? Victoria factor, right? So you have x squared here, it will cancel the x squared on the denominator, x squared here will cancel out the x squared on the denominator here. You agree? So if I simplify it, I just write here 1, and this 1 over x squared, I do not know how to simplify anymore. Are you following me? Good. So what you get now is that this x squared is not 0, correct? Because it's just for a moment it's just a large number. For any x that we plug in just larger and larger values. It's a number, and this is a number bigger than 0. Therefore, I can cross it out and reduce it to 1, correct? And now what I have is 1 minus x, 1 over x squared over 1 plus 1 over x squared. And then as I make x larger, this is disappearing to 0. So we have 1 minus 0 plus over 1 plus 0 plus. Notice that the denominator is slightly larger than 1. The numerator is slightly less than 1. So we're approaching 1 from below. Yes, from below. But the answer is 1. Now, if I were to graph this curve, imagine graphing it, but of course, you don't do it actually, right? So imagine I graphed it. And then when I say x going to infinity, it's the equivalent of pushing the screen to the right, very far to the right. What does the graph look like if I push it very far to the right? I'm not asking you in the middle. It might be slightly more complex in the middle, but you push it very, very far to the right. What does the graph look like based on this prediction? Well, if I scroll to the right, what is the shape of the graph? Nothing, right? the landscape. Imagine it's a one-dimensional landscape. What does it look like if I move the camera very far to the right? You understand my question? So Mirasov says going up, so you're saying it's increasing. Only, you see, here is my x, right? My x is increasing. If x is larger values, that means that I'm looking on the x-axis to the right. And Pavel, yes, very good. It is a straight horizontal line. Y equals 1. You see, if this is y equals to this complicated expression, this looks like y equals 1, because in the limit, those numbers are very similar to 1. You see, this ratio is very close to 1. Does it make sense? So I don't have to visualize the graph in the middle, but if I move very far to the right, that's what we're saying here. For very large values, think of it again, imagination, guys. Here is one large, oops, sorry, here is one large value of x. We are roughly 1. Here is another very large value of x. We're roughly at 1. See, here is a 0.1, here is 0.1. If x is large, we are just simply altitude of this curve is always at 1. So for any large x, the altitude is 1. Yes? So it's just a horizontal line, essentially. Actually, the way we go to it is like this. Understand? So we're climbing. I know that because it's 1 minus some small positive number and the denominator 1 plus. So it's always a fraction smaller than 1. So I am climbing to this level line. But if you're very far to the right, you will not notice it. It will be such a slight climb that it will look to you like it's horizontal. Make sense? And that's our definition of yes, Rafi, go ahead. What can I say? Anything here confusing, or you get it? No, because look at it. When I factor, it's x squared over x squared, right? So I cross them out. It's 1 minus 1 over x squared, where x is large, so this is almost 0. 1 over x squared is almost 0. So it's 1 minus a positive small number, and on the denominator, it's 1 plus a positive small number. So essentially, we get 1. If you push x towards minus infinity, if you push the graph to the left, you get the same exact pattern. You can also notice that because the function is even, it's symmetric around the x-axis, or around, sorry, the y-axis. Okay, so this is what we call an asymptote. Y equals L is a horizontal asymptote. Now, let me just try to explain to you what is a horizontal asymptote. It's very similar. It's this is what you do, right? When you're trying to explain to somebody, well, something unfamiliar to this person, you might say, this person was as strong as a buffalo or as big as an elephant, right? So that, in other words, you are talking to someone who has never seen that person, but knows what's a buffalo and what's an elephant. So mathematically, the buffalo or the elephant are like the asymptotes. You understand it? It's the asymptote of the person that you're trying to describe. Or when you say to a girl, your eyes shine like 2 moons, you're saying that her eyes, the asymptotes for her eyes are moons, okay? Or a moon. 1 moon is for each eye. You understand? So it's an analogy to make something understandable. So presumably you take a complicated object and try to compare it to an object that you understand much better, possibly a much simpler object. So you look at this function, it's complicated, but y equals to 1 is not complicated. Do you understand? It's also the same thing that you do when you look at clouds, when you say the cloud looks like a unicorn. What you mean is that in this complicated shape of the cloud, you recognize a much more familiar and simpler shape of a unicorn. Good? Asymptotes are just analogies, so it's a very, very loose word. Okay, and let's see if you can calculate a horizontal asymptote for this expression here. You see 2x cubed plus x minus 1 over x cubed plus x squared plus 5. Let's see if you can take the limit to infinity and tell me what happens if I move to the right.
Wait, so right now we're just finding the horizontal asymptote for that function?
Yeah, for 2x cubed plus x minus 1 over whatever the denominator is. Just find the horizontal asymptote, or maybe it doesn't exist. Maybe I just asked you to find something that's not there. By the way, guys, you see, why would you forget about this problem? Find horizontal asymptotes. You would forget if you don't understand what is it that we're doing. What am I asking you? In very simple language, find horizontal asymptote. What am I asking you? You see, if you cannot answer that, then you're not following what's happening.
I would say we will find the value of x if it's horizontal, yeah?
Yes, but it's very abstract what you're saying, right? Value of we do not value of x, we make x large. What are we really thinking? You see, I can tell you what I imagine. I imagine, for example, a train. A train is moving further, right? Further.
Okay.
And then and I look out of my window and I look at the landscape. You understand? You have to imagine something. If you don't imagine anything, then it's meaningless, right? And you're departing from the country that you loved, and you're never going to see the person that you used to love. They're all left in the back, right? And you're looking at the landscape. It's and the ravens are flying over it. And then you notice how the landscape is going up and down, up and down. And then suddenly, if you say there is a horizontal asymptote, what are you saying about the landscape? You are traveling into what? You are traveling into. If it's horizontal asymptote, it means that your landscape is now a. When it's like this, what's the landscape? What's the landscape?
Horizontal?
It's a hilly, and then it's not.
Yes, exactly. It's
So
what's
it's the
hilly.
limit.
Oh my God, guys, right? You should go out of New York sometimes, right? So you might travel to the mountains. That's when it's hilly. And when you say there is a horizontal asymptote, you are saying that the landscape is a plane. You are now in the Russian plains, the great Russian plains, and you go on forever, and you just have plain forever. Just you don't see where it's over. We need to, you see, that's what happens because you don't listen to good music, don't read good books, and don't think too much, right? That's just your imagination is not developed, and then that's why you survive, because you will not have a car accident, right? I had many times where I stopped seeing or hearing anything, and I'm just in a different world, right? That happened to me many times. I have to really try not to do that. Okay, good. So we are trying to see if the landscape, as we traveled very far away from our homeland at 0, we're trying to figure out if the landscape is becoming flat or not, right? So that's how you know you are in Russia, or in some places in Russia. You understand? So what do we do? You know what, when I see this equation, you know what I think about? I think of Anna German in the song, "I will hear you 1,000 miles across." We are an echo an eternal echo of one another. Because what does it mean? You move very far to infinity, right? Very far away from something, only to go back home to zero. So you got two, wonderful. So you have a landscape at 2. Let's do it together, guys. So what we do is we look at the numerator and denominator and factor the leading term from each. I factor x cubed from each of them. You see that? X cubed, and then it will be 2 plus x over x cubed minus 1 over x cubed. And on the denominator, it's 1 plus x squared over x cubed plus 5 over x cubed. And I simplify the x cubes, I can cross them out because it's a number divided by itself. It's 1. It's not 0 because x is large. It's 1. And I have this numerator and this denominator. Now, if x is very large, this is 0, this is 0, this is 0, this is 0. So the answer is essentially 2. Do you agree? That means that if I pan my camera, if I move along this curve very far to the right, I will see the horizontal line y equals 2. You will not tell the difference. If you graph it on the computer and you scroll far to the right, scroll past 100, 1000, etc., it will look to you indistinguishable from a horizontal straight line, y equals to 2. You agree? Here is another simple question to see if you understand it. So imagine that you have an AKG. You know what's an AKG, right? It's something that maybe from your phone is attached to you for all your entire life, right? What's the limit? So the graph of the AKG is beep, beep, beep. What will the graph be showing once you move very far to the right in time? So there is time, and then beep, later beep, time. What is the AKG going to show later on as we move farther to the right? Well, maybe a 0. I'm not sure where you have it, but in particular, what will it be? You can also speak it with, yes, it will be, right? And that is that is the horizontal asymptote. Okay, so there is this complicated graph, but eventually just a flat line. Good. So.
And the person dies.
Sorry?
Yeah.
Well, I mean,
Yeah.
if you imagine this AKG attached to the person, even afterwards, maybe there are some bumps, who knows, but really it's just...
no, but still, I refuse to consider that. If a person died, they died. No reviving, no attempts at reviving, no nothing. Just they died. Sorry to be salty.
No worries. So, where are we, guys? Okay, so again, I want to emphasize that there is nothing special about horizontal lines. If you have a line with a non-zero slope, it's going to be called an oblique asymptote. Yes, well, I mean, if it's forever, right? If you just flat for a while, Christian, and then it starts moving again, that's like in the movies, right? It's like it disappoints. It's like a tricky calculus question. When it's a flat line and then it begins to move. In those soap operas, it's just you haven't watched it long enough. It's not where it begins to be a horizontal asymptote. Okay, so again, back to this. If the slope is not 0, that's called an oblique asymptote, and all it means is that my curve looks like a line. Okay, and then you can have a quadratic asymptote. That means if it looks like something like y equals to x squared, that is a quadratic asymptote. Make sense? It looks like x squared eventually. So it's also a simple curve, right? X squared, x cubed might be simple curves so that you know what they look like, so you can take them as asymptotes. Again, asymptote is only, understand the word, guys. Asymptote is an analogy, right? Asymptote is the elephant, is the thing that you recognize that you can compare less recognizable foreign things. Good? So here is, let's try this, guys. Can you find the asymptotes or whatever that might be of this expression? Can you guess what type of asymptote it might have? If you prefer, try to calculate limit as x goes to infinity and limit as x goes to minus infinity for this function, please. You can do that first if you prefer. So Alex says the limit is infinity. Positive, that's okay. To both directions, minus infinity. And what does it mean about the landscape, guys? If you're getting a limit that's infinity when you move to the right, let's try this together, right? We can do that easily, right? We can factor out from numerator x to the 6 and denominator x to the 4. And when we simplify, we're left with x squared times this expression, right? So this is just going to be when I write infinity times 1. What I mean by that is that I have a number that's increasing and getting very large times something that looks like 1, essentially, right? So it will be clearly a very large number. So when I say infinity times 1 is infinity, all I'm saying is that multiply 1 by a large number, you get a large number. And boundlessly large, okay? So we have infinity. Can we have a horizontal asymptote if we get infinity here? Have you spazzed out, guys?
I'm gonna say no.
Okay, James, why no?
Well, I would say, for my first reason, right? Because it's affinity, right? Unless it's still affinity, right? But unless you have, like you said, it's a limit, right? Plus some minus, you can also get one number and also find the in between those two values of the limit. So negative affinity and plus positive affinity. So even it's still affinity, but it's still in between.
Tell me this, you are in this train. The train is riding along this landscape, right? You look
Yeah.
out the window. What do you see? What sort of landscape do you see?
Buildings.
No, so from this function, transport yourself out of this concrete jungle. I'm assuming you are in New York.
Yes.
Yes, well, too bad for you. You might have never seen anything better.
I would. All right.
All right, so guys, what sort of thing do I see out of my window? So the fact that it's infinity, thank you, James, by the way, I really enjoyed what you said there. So infinity here only means what? If I'm not, definitely my altitude is growing. Do you agree? This just means this is the altitude. This communication here is telling me what's my altitude. I move horizontally farther and farther, and my altitude is clearly growing. So I cannot be moving on a plane. If I were moving on the plane, my altitude will not be changing. You understand? This just means altitude is boundlessly growing. I'm just always going up, forever only up. Make sense? So the question is, what is the landscape and what do you find yourself? And then we can investigate it using long division. Here is long division, guys. Do you remember long division? You might actually see it without it right away, but here, I want to see how x to the 4 plus 1 divides into x to the 6 plus 1, okay? So I ask myself, by what do I multiply this expression to get x to the 6? Clearly by x squared. So x squared plus x squared is just x to the 6 plus x squared. You follow me, guys? I subtract, and then the x to the 6 are crossed out. I have minus x squared plus 1. Now, this can no longer be divided by x to the 4, so it's a remainder. Look at it. So I have x squared plus this expression. Do you see that this expression goes to 0? The power here is smaller, so this expression goes to 0. So if I move to the right, it looks like x squared. Look at it. Move to the right, it's always x squared plus something. And that something that I add here is becoming insignificant if x is very large. Do you see that? So essentially, what do you find yourself at? Your asymptote is quadratic. It's y equals x squared. You are on a roller coaster, so you're moving like this. It's a roller coaster without end because you're never going to fall. You're just climbing steeper and steeper, like this, right? A quadratic. So
but you're not going to escape from it either, and yeah.
Alan, what do you mean?
Even though you can't like fall off or you can't get out of the roller coaster. Hence, somebody who hates roller coasters.
You cannot get out of a roller coaster. That's your life, right? You're carried onwards. So, well, that's do you understand, guys? Long division. Do you understand what I calculated here? That's supposed to be prerequisite material. So hopefully you know how to do long division. If not, we can of course talk about it as well. But you understand how I carry this procedure? I could have actually, just by looking at it, I see that it's x to the 6 and this is x to the 4. I can see that this is 2 degrees bigger than the denominator, so I expect it to be a quadratic asymptote. You understand why it's an asymptote? Because when I can factor out x squared, and then it's x squared plus a residue that when x is large melts to 0, either to plus or minus infinity, it's 0. So it means if I move away from the center, if I move very far to the right or very far to the left, my landscape looks like the same, like the landscape of the square function. It looks like a U-shaped landscape. You understand? Like parts of a U-shaped landscape. Do you follow? Are you with me, guys? The class is almost over. It's okay. All right. So here is, I suppose I'll stop recording now. And I want to show you something actually that I heard a few years ago in a car, and I was very surprised by what I heard. I wonder if you will understand why I was surprised.